Welcome to Math TV with Professor V. It's Wednesday, December 21st, 2022, and here's the integral of the day. We have antiderivative of 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3 dx. So right off the bat when I'm looking at this, I notice that the degree of the numerator is the same as the degree of the denominator. So before we proceed, we need to long divide. The degree of the denominator needs to be higher before we can decide what sort of technique to employ. So here we go, 4x squared minus 4x plus 3. Divide that into 4x squared minus 3x plus 2. So 4x squared goes into 4x squared just once. Then I multiply that through, so this will be 4x squared minus 4x plus 3. I don't like the mess. And then we subtract bottom row from top. The terms on the far left should cancel, otherwise you messed up. Negative 3x plus 4 is x, and then 2 minus 3, negative 1. This is our remainder. So now our integral is equal to antiderivative of just 1, right? That's my quotient, 1, plus, here's my remainder, x minus 1 over 4x squared minus 4x plus 3 dx. All right, from here, let's look at each term that we're left with. Antiderivative of 1, we can deal with that, no problem. X minus 1 over 4x squared minus 4x plus 3. Probably your brain jumps to trying to find the partial fraction decomposition, but you're stuck because this denominator here, this quadratic, is prime. It does not factor, so we can't utilize partial fraction decomposition. What do? We do not sit there and cry. Instead, we're going to complete the square. So that needs to be your backup plan when you have a quadratic denominator that doesn't factor. Complete the square. How do I mean? So 4x squared minus 4x, that's almost ready to be a perfect square trinomial. It's just 4x squared minus 4x, I need a plus 1, right? In order to factor it into 2x minus 1 quantity squared, which is fine. I'm going to borrow that 1 from the 3, and then I have just plus 2 left over after I complete the square. All right, so now let's rewrite where we're at. We have integral 1 plus x minus 1 over 2x minus 1 squared plus 2 dx. All right, what to do from here? Well, we're going to utilize a u substitution, and then we'll proceed from there. You should start getting feelings of like tan inverse is going to happen because you have some variable quantity squared plus a constant. Okay, so we're going to make it work. Oh, yes. So we're going to go ahead and let u equal 2x minus 1. That means du is equal to 2 dx. So 1/2 du is dx. All right, everything's looking good. Just to kind of tidy things up, I'm going to integrate the 1 right now. So that's just x plus antiderivative. In the denominator, instead of 2x minus 1 squared, I just have u squared plus 2 now. Dx is equal to 1/2 du. Du, put the constants outside. That's what I always tell my students. And then, oh no, what do we do about this x? You're going to come right here where you decided to make your u substitution and solve for x in terms of u. It's not hard. Add 1, u plus 1 is 2x, and then that means 1/2 times u plus 1 is equal to x. So that's what's going to get substituted right there, 1/2 u plus 1 instead of x, and then I still have minus 1. All right? I know, a lot's going on, but once you've seen this technique applied a couple times, then you get used to it. The first time might be somewhat shocking, I understand. Okay, we've got x plus 1/2. Let's tidy this up. We have 1/2 u plus 1/2 minus 1 over u squared plus 2 du. And then, you know what I'm noticing? So this is negative 1/2, right? Yes, that's negative 1/2. So I can rewrite the numerator as 1/2 times u minus 1 over u squared plus 2 du. Are you with me? If I lost you, this is what happened that I didn't write out. We have 1/2 u minus 1/2 in the numerator. So then just take out the 1/2 and you have u minus 1. Okay, very good. Now, this constant wants to hang out with its other constant friend outside, so let's let them be together. So we've got x plus 1/4 integral. Now what am I going to do? I'm going to split the two terms. We have u over u squared plus 2 du minus 1/4 integral 1 over u squared plus 2 du. Each of these we're going to tackle separately. Are you ready? Great. Okay. When you're used to doing these integrals and you're in calculus 2, you should be able to do this in your head. I know, shocking, right? No, you probably are fine. You need another substitution. We already used up u. You could let t equal u squared plus 2. Then dt would be 2u du. So 1/2 dt is u du. All I care is that I'm going to pick up an extra 1/2. And then I'm going to have 1 over t in the denominator, which is going to give me natural log absolute value of t. This I can all see in my head. If you can't, take the time to write it out separately. But I encourage my students, if you can see this, you can keep the 1/2, keep track of it, and execute it well. I don't need to see the substitution. You don't need to write it down, okay? These integrals get complicated, so if there's little basic things, do it in your head. What does that mean? I have 1/4. I'm going to pick up another 1/2, so I've got 1/8 ln absolute value of t. I don't need absolute value because u squared plus 2 is always going to be positive, okay? Minus 1/4. This you need to recognize. If you don't, you're in trouble. Tan inverse, yeah? Okay, good. The constant a squared is rad 2 squared. So we're going to have 1 over rad 2. Little peculiar, but it's all good. Tan inverse of u over rad 2. And then now at long last, we can put plus c. All right, then cleaning things up because we need to rewrite our original variable into our final answer. So we've got x plus 1/8 natural log. U squared plus 2. You know why that seems familiar? Because before we completed the square, this was u squared plus 2, which we had as 4x squared minus 4x plus 3. So it's just the original denominator, 4x squared minus 4x plus 3. Minus 1 over 4 rad 2 tan inverse u was 2x minus 1 over rad 2 plus c. I know, but I've been gone for a little while, been in a cave, grading finals and whatnot, and I finally emerged, so I wanted to just make quite the comeback. Do you know what I'm saying? Yeah, when did we stop rationalizing denominators? It happens at some point in calculus. No one officially says you don't have to worry about it anymore, but you don't always have to worry about it anymore. Do you feel naughty? I don't. I think it looks way better. 1 over rad 2 looks nicer than rad 2 over 2, if you ask me. Okay, anyways, I suspect it comes from when calculators were not able to, do radicals, and you would have to use a table of radicals, so you needed the denominator rationalized. I don't know exactly. I should look into it. Anyways, if you enjoyed the video, give it a thumbs up. Subscribe to my channel if you haven't already. I know we haven't discussed so much, but I hope you all caught the World Cup finals last Sunday. Oh my God, it was so thrilling. What a game. What a game. And during break, I'm going to work on just filling in more content on some of the playlists that I have not completed and making more integrals of the day, of course. I have an episode of Ask Professor V that's on the docket. So stay tuned. You can see what I'm up to on Instagram and TikTok at Math TV with Professor V. And you can also click join to become a member of this channel and get access to exclusive content as well as my Patreon. So take care, guys. Hope everyone's doing well. Stay safe, healthy, warm, happy. I'll talk to you guys soon. Bye.